Oh, hi guys, welcome back to this video series. Now we have previously been discussing how neutrons, how alphas, how betas, how gammas, and how the fission fragments in the form of swift ions can damage the cladding or any form of material in general. We've also discussed how, especially the fission products coming off a freshly fissioned atom can damage the nuclear fuel cladding. Just to give you an intuitive sense of it, with not so much math, because that's kind of been discussed before, especially when the neutron impacts onto the pKa. So now we've discussed what happens to the metals containing the fuel. So most of it has been done in all this discussion has been done so far. We'll talk about reactor pressure vessel, we've talked about cladding, but we have not discussed the uranium oxide fuel itself. So these are the barriers. This is the cladding, this is the reactor pressure vessel. We have not discussed the uranium oxide itself. Now, previously we've discussed why embrittlement is important for cladding and the reactor pressure vessel, because we don't want them to rupture or leak suddenly. So these embrittlements, the stress strain curve, these are very important for the cladding and the reactor pressure vessel. But what about the uranium oxide fuel? Okay, what about the uranium oxide fuel? How does it differ from metals, and what material properties are important? Well, the fuel itself doesn't have to handle any kind of load. It's just sitting around inside the cladding, housed nicely inside the cladding, like so. Okay, so the fuel pellets are sitting around nicely inside the cladding. They don't really handle as much stresses as a reactor pressure vessel or cladding. So embrittlement is not really that important, but even if the fuel cracks inside the cladding, so this is the cladding that's containing the fuel, and it will be a cylindrical shape outside. Yeah, a cylindrical shape outside. So even if the fuel cracks under load, it's not that important as long as it's contained within the cladding and the reactor pressure vessel. So all the nasty fission products don't leak to the outside. Okay, what's more important? Well, for the fuel, the more important parameter is heat conduction. Why? There's a heat transfer, specifically speaking conduction. Why is that more important? Well, the job of the fuel is to conduct heat to the cladding, and surrounding the cladding for a light water reactor, there'll be water on the outside, either pressurized water or some cases a thin film of water in a boiling water reactor, and that is you're supposed to transfer heat from this fuel into the water. So that's why heat transfer properties are way more important for the fuel as compared to the reactor pressure vessel. Secondly, if the fuel itself gets too hot, the middle part of it can melt. There's part of it can melt, and that's pretty not a good thing to happen in general. So heat is generated in the nuclear fuel as the uranium-235 undergoes fission. How can we ensure that the heat is conducted well enough to the coolant so that we don't have the melting problem and we don't have other funny things happening? So yeah, melting is one of the core considerations. Well, for one, we can make the fuel metallic in nature, since metals actually conduct heat pretty well. However, that's not used for light water reactors, so uranium oxide is used. I won't discuss the reasons in depth, though there are actually reactors making use of metallic fuels or molten salt in some other cases. Yeah, we can discuss the pros and cons of each in maybe future videos, but for now, we just assume we are stuck with oxide fuels because these are the commercially available ones, the most common that we find today. Okay, so the ceramic itself, when I talk about oxides, they're also called ceramics. The ceramic itself is not good for heat conduction. So how do we ensure good heat transfer properties? Well, we want to maximize surface area. Yeah, we want to maximize the surface area. And from Fourier's law of conduction, Q equals to K dt dx. This is a one dimension of Fourier's law of conduction. You can see the heat flux, which is the heat transfer rate over area, equals minus K dt dx. This is the conductivity, this is the temperature gradient, and this is the area. If you're not sure what it is, you can look in the video description below. There's a Khan Academy video. So anything by Khan Academy is usually good stuff. But yeah, we have putting some videos of Fourier's law in the description below. So I assume we know what it is, so let's continue. Yeah, so the idea is to maximize the heat transfer and minimize the temperature gradient. So there are two things we can do. Either we increase this heat conductivity, or in our case it's kind of fixed because the material is already fixed at uranium oxide. The other thing to do is to increase this surface area. So how do we increase this surface area? We use small fuel pellets. So you can imagine for a very large fuel pellet, alright, as compared to, let's say, a 10 kg amount of fuel in one large fuel pellet. If you use this 10 kg in small fuel pellets, you see that the small fuel pellets, these small fuel pellets, they have way more surface to volume ratio. So they have a higher surface area per unit volume. That's why we tend to want to use small fuel pellets. So that's why we have in a fuel rod, in a nuclear reactor, we have very thin fuel rods arranged in a bundle, and inside you have all the nuclear fuel. Alright, just gonna draw it like that. Dum, dum. So why are they designed in a fuel bundle? It is because we want to maximize the heat transfer properties. There's of course an upper limit to how small you can make these fuel pellets, because if it's so small, then you will have all these if you want to make the bundle so small, you got to make like these small needles, and there's an upper limit to that based on, well, if it's so small, it's going to be fragile. If it's fragile, you're like allowing some of the fuel to leak, and that kind of defeats the purpose of having cladding in the first place. Okay, so yeah, we want to have fuel pellets. And the other thing, if you want to decrease the temperature gradient, is to decrease the spacing between the fuel and the cladding and the water. So the fuel, okay, say you have a fuel layer here, we have a cladding layer here, and we have a water layer here. We want to minimize the distance between the fuel, the cladding, and the water. Fuel, cladding, and water. Yeah, we want to minimize this spacing. But but the thing is, inside the cladding itself, there is some helium gas, and there is some spacing. There is some spacing allowed, and you might wonder, why do we have to have some of the spacing in the fuel. Well, the thing is that when the fuel undergoes nuclear reaction, we know from neutron damage that this can cause a lot of vacancy plus interstitial pairs. And when these vacancies and interstitial pairs settle down, they can form voids, and these can cause swelling. This can cause the fuel to swell. They can also cause the metal to swell, but especially in the fuel, that's also a very important phenomenon that can happen. Now, you don't just have this happening. We have fission products as well, or the fission fragments, and then they are deposited in the fuel. They can also cause swelling, because some of these fission products are gases. Now, gas has obviously a very large volume, so these gases will lodge themselves in the fuel and cause the fuel to expand. Sometimes the fission fragments consist of solids, but these solids in general have a lower density as compared to the uranium oxide here. So we have a lower density solid being lodged into the uranium oxide, so the fuel will also swell because of the solid fission products. So the chemical composition of a fuel changes over its life due to the nuclear fission reactions going on. So the density of the fuel may change for these reasons. All this cause swelling, so the fuel will expand as it goes through the reactor. And if you don't give it enough space, the fuel will push itself into the cladding and cause it to crack. So there is a kind of a trade-off here. You want to give the fuel some leeway to expand, but not so much that the conduction is rubbish. So you can imagine the light water reactor fuel changes a lot during its lifetime, and there are many simultaneous effects going on. So let's go through this step by step. And in this video, we want to talk about the initial phases of reaction. So we're going to talk about thermal processes and thermal expansion. Now here's some common sense. When things get hot, they expand. Right? When things get hot, they expand. And what will the temperature profile in the fuel look like? Now, if we solve the heat transfer equations, we know that the hottest part is in the center of the fuel. Okay? So this is the center. So let's say this is 0, and then r equals to 0 is in the center, and it's a radius of r over here. There'll be some kind of curve that's downwards. Regardless of the shape, the highest temperature is always in the center. Okay, especially when we have a uniform heat generation inside this fuel pellet. So if we solve Fourier's law, the differential equations in 3D, we should be able to see something like this sort of temperature profile, and it's on the coolest outside and it's the hottest inside. How hot is it on the inside, you may ask? Depending on the reactor type, it can be from, the center part can be from 1000 to 1600 degrees C. The outside is about a toasty 300, 350 degrees C, or slightly maybe more than that. So with all these temperature differences, the inside of the fuel will expand way more than the outside of the fuel. With this kind of stresses going on, what does the fuel do? Well, the first thing to do is that the fuel will crack because of this temperature differential. It cracks because the pressure being exerted on the outer layers by the inside of the fuel. It cracks because the outer layers are experiencing the stresses caused by the expansion of the inside of the fuel. And how does it crack? It will crack, okay, let's say you have fuel here. It will crack along this direction. Okay, it will crack this way. And why does it crack this way? Well, we'll probably want to discuss more in the next video. So thanks for watching. I'll see you guys there.